Hi, Abigail.
Hello, how are you?
Great, how you doing? Hi, Austin. Hi, Christopher. Video. Let me open up the chat. And let me share my screen. And let me go the second section. All right, let's take a look at the syllabus. All right, can you all see my screen?
Yes.
Yeah.
All right, awesome. Thank you. All right, why is this not? There we go. Okay. All right, so let's see. Right, so we're starting week number 10. You're still working on the assignment for DB7 and DB8, and I've moved the due date for this coming Friday. And again, those are kind of like going to be treated as one big assignment, where the first half was the setting up the connection to the database programmatically using Java. And the second half was introducing you to one of many technologies that allow us to create some kind of user interface that we can interact with the database. Looks like most of you have been able to connect to a database and retrieve data, either using JDBC or ORM, which is great. I know there's a few of you that are still struggling through that, and that's fine. The TAs and myself are going to be helping you throughout. Please come this tonight to the office hours if you have not yet been able to work through the database connection. I see many of you have asked questions on Piazza about the user interface, but a lot of you have been able to work through those, trying to debug it. I know it's a brand new technology for you, so we're definitely here to help you out through any challenges you might have. And we're going to be extremely lenient with these two assignments, right? They're only here to introduce you to these technologies and how you might use them for connecting to database and getting started working on your final project. Okay, so these are just tools for you to build on and start building something, right? Obviously, you need to be able to connect to a database, and you need to be able to display something on some screen, right? So yeah, these are more like tools for you to get going. Okay, so we're gonna get back to some of the standard topics that you cover in a database course today. Well, definitely ORMs is pretty standard, right? Just connecting programmatically to the database. So assignment number 7 is pretty standard. Assignment number 8 is a little bit off topic, but not much, right? You do need to display that data somewhere, and it's a very common technique of building data-driven application. In this particular case, it's a data-driven web application, but it could have been a data-driven desktop application or a mobile application, whatever you want, right? You're free to do whatever you want for your final project. But I'm giving you a tool, right, to build web application, since it is kind of my forte. So let's get back to some more traditional topics that for databases in general. We'll talk about this week. We're going to be talking about transactions and indexing. Okay, and I'm going to introduce the assignment today, but all assignments are now going to be due on Friday, right? So the assignment that we're going to introduce today is not going to be due this Friday. It'll be due the next Friday, right? April 2nd. Okay. And so the general topic of today is optimization, right? And how is that we can optimize our database, right, to perform better, right? To make sure that whatever it is that we store in the database, it can be readily retrieved whenever we need it, right? And so there's going to be basically two topics really this week. One of them is, how can we improve performance by using indexing, right? How can we organize our data in such a way that we can retrieve the data very, very quickly? And the second topic, which is somewhat related, is transactions. When, how do you deal with the fact that you're not the only one using the database, right? If for any particular database, there will be dozens, hundreds, thousands of users, interacting with the database simultaneously, right? So how do you deal with that? Okay, so those two topics going to be talking about this week. All right. So yeah, so and the assignment is going out today, but it'll be due not this Friday, the following Friday. Right. Also, this later this week on Friday, there will be the quiz number 6. It will be regarding the object relational mapping assignments that you worked on DB7. Yeah, DB7. Which it's going to ask you questions about the ORM, about mapping, and using the creating repositories and and retrieving that data and interacting with it, saving, deleting, find all, that API, and it'll be open book like always. And so just familiarize yourself with that content, and especially what you've written for the assignment, and you should be all good. Okay. All right. Any questions on the schedule?
I have a question about the homework. Can I ask right now, or should I post
something? Is it a generic or is it an open or very specific question?
I'll just ask on Piazza. It's kind of generic.
Yeah, so come by the office hours tonight at 7:30, and we can work together and take a look at it, and maybe you can share your screen, and definitely that's a place for us to chat.
When does it end? It starts at 7:30, right?
Yes, all office hours start at 7:30 on Tuesdays and Thursdays. Okay. You also give me if the office hours don't work for you, because it's a weird office time zone for you depending where you are, feel free to reach out to me at my personal phone number. That's my personal phone. Please don't share that. Just text me, and we could jump on a quick call or maybe Zoom, and if I'm available, I'll we can definitely have a quick chat. If I'm not available right away, I can you can leave me a message and I'll get back to you. Okay. All right. Okay. So let's talk about the material. So as always, we are going to be. We typically we introduce a topic by the use of an assignment, right? And so we're going to be introducing the assignment today. Again, it's not going to be due till not this Friday, but the following Friday, April 2nd. And so there are two topics covered here, right? The first half is about performance through the use of indexes, and the second one is transactions. So two topics somewhat related. And like always, right, we're going to first demonstrate a few steps where you're going to follow along, right? And it's fully implemented and it's been vetted and whatnot. And then those skills that you practice, right, where we handhold you the whole way through, you're going to then turn around and there will be a now you try section, right? There'll be a now you try section where we ask you to do almost the same thing that we walked you through, but slightly different, right? So for instance, we're going to walk you through adding indexes and transactions to the blocks table, and then we're going to ask you to do the same thing for the posts table, okay, on your own. We'll give you some hints on what to do, and you can follow along. Almost the same exact steps that you did for the blogs. You should be able to do them for the posts table. Okay. So first of all, we ask you to import the database that you've been using for a couple months, right? So same database, and then that will be your starting point. Okay. Then for the first half of this assignment, we're going to explore the effects of indices on the performance of interacting with that database. Okay. So first a word on indices. What are they? What is an index? Okay. So an index, you know, if you think about a book, right, you'll notice that at the end of some books, you know, typically about on a book on some technical book, right? Usually at the end there will be an index, right? And that index usually will have, you know, things like maybe terms, right? And then next to those terms, it'll have the page where that term appears. Okay, and so the intent is that those words, right, they appear in the original content of the book, right, in pages, you know, 123, 248, whatever, right? And so you have the big content of the book, and then you have this index, right? The book might be 1,000-page long, whereas the index might be, you know, maybe 4 or 5 pages long. Yes, and then, but it's referencing where can you find things in the original book, right? And the intent of the index is for you to very quickly find things. It says, okay, you can find this word or this term defined in page 342, right? So you can, you know, go jump page 342, open it up, and then it says, oh, there's the book, there's the definition, right? So that's the intent of an index, right? The index is so that you can quickly find things. Imagine if you didn't have the index. How would you find a word or a particular term? Well, there's the table of content, which is somewhat give you a hint of where you can find certain terms. But imagine you didn't have table of content, you didn't have the index. The only way to find something is to read the book. You have to go through the whole thing, right? So we see that indices, you know, can definitely help us, you know, improve the performance of finding things in the original content, right? So same thing, indices can help us find things in tables, right? So just like an index, it's like a mini book, right? It's a summary of a book of 1,000 pages summarized in just 4 pages, right? 4, 5, or 10 pages, right? It's a mini book that only has the very important stuff and the terms and pointers or references of where you can find the real content. Indices are the same thing, right? You have the main table that has all the main content, and then you can have an index where it's a small version of the original table, where it's compact but it has references to the original records, right? So if you're looking for something in the table, instead of, if you have no index, then the only way you can find anything on the table is that you have to go through the table, looking and comparing for something that you're looking for, maybe a piece of text or maybe a particular field that has a specific value. The only way to find anything is to go record by record, right? And doing what we call a linear search, right? You search linearly, right, all the way through. And the problem with that approach is that it's very susceptible to the size of the table, right? So on average, right, if you double the size of the table, on average, you can expect that you're going to take twice as long to find anything on the table. So it's very susceptible. It's linearly. That's what we call linear search, right? It's the amount of effort grows linearly with the size of the table. Okay, so there are many better solutions to this instead of doing linear search, right? So indices are a means of improving performance. Make sense? So it's a small copy of the original table, which has been organized by the fields by which you want to be able to find something. Let's see, there's a question on the chat. Is the select query a linear search? If you don't have indices, then yes, it's a linear search. If you have indices, then it's not a linear search. Yeah, that's the point, right? And we're going to compare today. Let's take a look at 2 tables, one that has an index and the other one does not have an index. and run the same query, do a select statement on the table that doesn't have index, and do the same query or the same select statement on one that does have, right, and see what the performance is. Okay. So yeah, so that's what we're going to be doing, right? But notice that indices not always are going to be, they're not always going to be beneficial, right? If they're exclusively being used for finding things or finding a specific word, if it's for finding a specific word, you can jump to the index, find it. Oh, there it is. I can finally go jump to the original content, and there it is, right? But if you are inserting, right, if you are inserting new content, say you want to insert a brand new chapter into a book, well, that means you need to not only update the content, the main content, in a brand new chapter. Well, you have to go and now update the index as well, right? Because that chapter is going to have a whole bunch of terms, right, and that needs to be parsed, and you have to re-update your index to have the new pointers to this new chapter. So you're going to get a performance boost for when you read the data, but you're going to get a performance hit, right, when you're inserting data. Same thing with the tables, right? When we read the data, we're going to see an improvement in the performance, but when you insert data into the table, right, we're going to get a performance hit. Okay, and so this assignment is the intent is to introduce to you what are the effects of using indices on various operations in the database. Okay, so all right, so the way we're going to do this is that we're going to take one of the tables that we've been working on for a while. We've been using the blocks table, the post table. So we're going to use those two tables, right, and then play around with some indices. Okay, so first we're going to import the database that we already had. Let's head over here and let's see, let's close these two, and let's create a connection. And let's see, let's import the data that the database that we already had, import from, I think the latest that I downloaded was this one, DB5, DB Design 5. So let me open that and let's do an import. There we go. Okay, so if I close that and I see my tables, I can look at the original content here. We had let me blow away these two tables. Let's drop those two tables. We're going to recreate them today. Okay, so here's the blog. Let's look at the content. So we have these 8 blogs. It's a very small sample of data, right? So we want to explore, right, what is the effects of having indices. Right, so the way we're going to play around with this is that we're going to add 3 new fields, right? One called type, status, and country code. It doesn't really matter, right? We're only going to use them to illustrate what happens when we have indices on these 3 fields and when we don't have indices, right? So I'm just going to copy this. Now I'm going to keep track of what I copy and execute, right? So right here, I'm going to run this. I'm going to run this, and this is going to add. Let me make that bigger. I'm going to run that. Okay, so that adds 3 new fields. These 3 new fields. Okay, and then I'm gonna add indices on these 3 new fields. Copy that. I'm gonna get indices, and the way you add an index is you say add index. Some databases are different. Some of them are create index. Some of them are add index. So each database might have a different syntax. But in MySQL it's add index, the name of the index, right? And then whether it's ascending or descending, it's going to organize the table, the index, not the table. The table stays the same, but the copy of the table, right, is going to be ordered by this index, which you know, when you say you have a dictionary, or say you have a phone book. You know what a phone book is? It's been a while, phone books, right? So phone books used to be these really fat books that listed users or people that had phones, right, or landlines, and it was the person, you know, maybe the name of the person, their address, and their phone number, and you could find people. I don't know, anybody seeing Terminator? How the Terminator finds somebody in the phone book, and so they might be several people that have, you know, several people that have the same last name, but usually those would have unique phone numbers. Yes. And so it would be very easy to search through a phone book because it was sorted. Imagine a phone book that was not sorted. The only way to find anything in an unsorted phone book would be to go line by line, do a linear search until you find the person by their last name. Okay. Now typically the phone book was sorted by last name. Okay. It was convenient because usually the information that you had to search by was the person's name, right? So you would find them by last name. If instead you had a phone number, then sorted by last name was really useless to you, right? So we say that an index is only useful if it's organized by the key by which you're going to search. Okay. If you want to be able to search the phone book by either last name or phone number, then ideally you would have two phone books, right? One that is organized by phone and one that is organized by last name. Okay. Or probably one big phone book and then two different versions that is sorted by number and sorted by last name, and then a reference back to the actual record in the phone book, right, of where to find the actual information. Okay. So here we have three indices that are going to be three copies of this table. That one is going to be ordered by ascending by type, ascending by status, and ascending by country code. And that is going to allow you to improve the performance if you search something by type, or if you search something by status, or you search something by country code. Okay. All right. So let's add the three indices. Let's run that. Okay. There we have those three indices on that table. The table is pretty small. It only has, you know, like 5 or 6 records. Right. Notice if we retrieve the blogs again, we run that again. Notice that we now have those three. We have those three records that weren't there before, fields that weren't there before, columns. Okay. All right. So now we want to be able to insert enough information, right? We want to insert enough records to be able to run some queries that are going to. We want it to take some time, right? We want to be able to measure, you know, how expensive one query is versus another. And, you know, with 5 records, it's not really going to be very relevant, right? So let's add hundreds of thousands of records, okay, to see something meaningful, right? So we're going to modify the create random blogs store procedure that we worked on a couple of weeks ago, right? That you should already have, but we're going to modify it so that it has our 3 new fields, right? The type, status, and country code. Okay, so I already have it here. Let's see, store procedures, create random blogs. There it is. So if we say alter, this is almost the same exact store procedure that we looked at a couple weeks ago. Let me make that a little bigger. The only thing that is different here is that I've added these 3 new fields, right? And when we and also I randomly generate those 3 fields. The type is a random number between 0 and 10. Status is a random number up to 20, and country code is 250 countries. Okay. And then I insert those values as well in the database. Okay. All right. So having that, we can invoke that store procedure to generate 100,000 records. Right. So we can go towards the bottom. I'm going to create that store procedure. We're going to use that store procedure to generate. We're going to generate 100,000 records at a time. Okay. So if we run that. We run that. It's going to take a while. Now, depending on your machine, if it's a brand new machine or it's an older machine, this might take a little longer. So this might time out. The server won't, will time out at 30 seconds. And so anything that takes longer than that, you're gonna get timeout error, which is okay. That's fine. You just run it. You can run it this multiple times until you reach some significant amount of records, right? And ideally, we would insert about, I don't know, like 500,000 records, maybe 500,000 or thereabouts. Okay, notice that it timed out at 30 seconds. We can count how many records we were able to insert. Okay, so we can run that, and it says that, count from logs, select count ID, and there it is. So yeah, so it was able to insert quite a few, about 100,004, 100,004 records. Let's run this just a couple more times. Yeah, so we want to have enough records in there to make our results somewhat meaningful. So again, this is going to time out at 30 seconds probably. Let's see. It's going. All right, let's do one more time. Maybe 200,000. Oops. Okay, while that's going, all right, there's a question in the chat. What is the biggest database you have ever seen, Professor? Oh, I had at work we had it was a Mongo database which was several gigabytes big, and it was very hard to work with because the way so you remember limit, right? Limit allows you to ask for so many records and say that you only want so many records to come up. And it allows you to skip also, like start at record number whatever, and then retrieve them more records, because we couldn't just display millions and millions of the records that we had. And the older versions of MongoDB had a bug where the skip that would allow you to jump, right, and paginate, it would actually need to iterate over those records and then position itself at a specific point in the database, and that would take forever. Right, as opposed to skipping it, was actually reading it, right? So it was very hard to work with. So we had to partition it into smaller databases so that we can, use it. It was a very cumbersome to use, but yeah, it was several gigabytes big. It had millions and millions of records. So anyway, so let's see how many we were able to introduce. Let's run this. All right, so we have about 400,000 records. Perfect. Okay, so we can start playing with this with some meaningful information. All right, so the way we're going to evaluate the performance, we're going to create two tables, right? That are going to be copies of this bigger table, right? One of them is going to have indices, and the other one's not going to have indices. Okay, and as we copy, we'll notice that inserting into the table that has no indices is actually much faster than inserting into tables that have indices, right? So let's demonstrate this. So for instance, let's create a table B1. Excuse me. Let's create table B1 here. So B1 is not going to have indices. So it's going to look identical to the blocks table, right? It's going to have ID, name, topic, created, user, type, status, and country code, right? It has the same exact schema, right? But has no indices. And let's create now B2, which is going to have indices, right? So let's copy that. And let's create B2 now. Okay, so now we have two tables, one with index, this one has indices, but the other one doesn't, right? And so key here is what creates the indices for B2. Okay, all right. So now let's look at the impact of using indices in the insert operations, right? So for instance, let's copy this here. Let's copy from the blocks table into B1. Right, so if we insert, notice that it's running. Notice that it's going. It's doing all the copy, right? And it comes back, and it took 2 seconds to do the, almost 3 seconds. So 2.902. So 2.902 seconds, right? To do the copy, okay? And we can verify that it copied all the records, 400,002 records. Okay. Now let's do the same thing for the other table, B2, right? That has indices, right? Has indices. Let's see how long that takes. So let's do that. Okay. So it's up and running. There it is. So let's wait a few seconds, and it'll come back and tell us, okay, this took 5.892. So 5.892 seconds. So almost twice as long, right? It took almost twice as long to insert into the table that had indices compared to the one that did not have indices, right? And it has the same number of records. There it is. So we have now 3 tables that have 400,000 records. So we see that inserting into a table can be expensive, right? As the analogy that I mentioned earlier, right? When you're inserting a new chapter into a book, right? We need to go and not only insert the new data, the expense of adding the new content to the book, but also having to update any indices that we might have. Okay, but for the most part, right? What we're going to be doing mostly, hopefully, or it depends, right? What we're using the tables for. We're mostly going to be reading data from the tables as opposed to inserts, right? And that depends, right? If you are doing mostly read-only operations in a table, then yeah, indices definitely can help you, right? But if you're working on a table where you're doing mostly inserts, actually indices might work against you. So you have to be careful whether you want to use indices or not. It depends on the operations that you're going to be doing. Also, if you're going to be doing individual queries, that when you go out to a specific record, then definitely indices can help you, right? But if instead you are doing queries where you're going to be retrieving a lot of data, right, a lot of records, right, then maybe indices can go against you, right? So it depends on the query, right? So first, let's look at a simple query where we are retrieving an individual record. Okay, so for instance, if we retrieve a single record from B1 that does not have indices, right? It does not have indices. It comes back with like 2.8 milliseconds right here, 0.0028 seconds, right? So this comes back to 2.8 milliseconds. Okay. Now let's do exactly the same query, but in the other table B2, right? That does have indices. So if we do that, the query comes out to be at 0.0037. Wait, it took longer? Oh, okay. So this one is oh no, 0.13 seconds. It's the second number here. I can't see. Duration. Fetch time. Okay, there it is. The fetch time is 0.0020. So this one was 13 milliseconds. So this was 13 milliseconds, and this one was 2 milliseconds. So this one was 2 milliseconds. Okay, so it's an order of magnitude, right? Slower to do it with without indices than to do it with indices, right? So definitely it can help you there. But not always, right? So let's see what happens if you want to retrieve something. If you want to retrieve something, but you use a range as opposed to an individual record, right? So if you do a range, right, it comes out to be 2.4 milliseconds, right? 2.4 milliseconds. So 2.4 milliseconds. And if you do the this one over here with the one that has indices, right, it's actually a little slower, right? It's 3.6 milliseconds. So 3.6 milliseconds, right? So depending what the query is, right? If you're doing, definitely you're doing an individual record and retrieving it, definitely indices will help, right? If instead you're doing ranges or you're doing something that is not unique, okay, then definitely that is not necessarily going to improve that much, okay? And that's going to be the topic of today, and which is going to spill over to this coming Friday as well. Okay, why is this happening, right? So you're going to be doing the same thing now. Now you're going to do a now you try it section here, where you're going to be asked to do the same exact thing we just did for blogs. You're going to do it for posts. Okay, you're going to create two tables of P1 and P2. You're going to copy over posts. You're going to insert hundreds of thousands of posts into the post table using create a store procedure that populates the posts. Okay, and here are in general the steps to follow. Right, you're going to add the same exact columns that we added to the blogs table. You're going to add them also to the post table. You're going to add indices for each one. You're going to add random posts and you're going to create a store procedure to populate hundreds of thousands of records of posts, right? At least 500,000. And then you're going to create two tables, P1 and P2, one without index, the other one with indices. And you're going to insert, you're going to copy from the posts to the P1 and check to see how much longer does it take to insert into the one without index and the one with indices. Then you're going to retrieve the data and see how long it takes to retrieve data from either one of the tables, and finally with ranges, and jot down the times. Yes. So all this that we've been writing, right? All these statements, right? You're going to save it to a file, right? And for the blogs that we did, that we're dictating what you're going to do, you're going to call it blogs. Blogs, what is it? Index, blogs index in SQL. Okay, and then you're going to do the same thing for posts. The posts index, that HTML. Okay. All right. So that's the first half of the assignment, where you play around with indices. So the second half of the assignment, you're going to play around with transactions. Okay, so let's talk about transactions. So transactions allow us to work together, right? Allows us to share databases, right? And usually it's not going to be just you using the database, right? Usually it's going to be dozens, hundreds, thousands of people, right, individually accessing the database simultaneously, and the database needs to be able to support this. One of the challenges of supporting so many people accessing the database at the same time is that we might be working on the same area, right, and we might be trampling over each other, we might be stepping on each other's toes. Okay, so imagine a Google Doc, right? Google Doc allows multiple people to work on the same document. Okay, now there's several strategies that we might take, right? One of the strategies might be, no, you cannot work at the same time, right? Only one person at a time. If I open it, I'm the only one using it, and nobody can touch it, nobody can even read it, right, until I am done, right? So that's one strategy, right? Multiple people can use it, but one at a time. Okay, so I open it, I do my work, nobody can read it, I'm done, I commit my changes, now they're permanent and stored in the database. Another alternative is that I am the only one who can write, but anybody who wants to read it, they can see the changes as they happen, right? And as I'm writing, they see exactly what I'm doing. Okay, that's another strategy. The other strategy is that we all can work at the same time, right? And as long as we are polite about it, right? You can say, well, I'm going to work way up here at the top of the document, and you're going to work way down there at the bottom of the document. And as long as that we're not writing over each other, then there's no problem, right? We can synchronize, we can be polite about it, right? And coordinate, okay? But what happens if we need to work on the same part of the document, okay? Either because we don't know that we're working on the same part of the document. You know, something very common that happens is in, you know, we're using GitHub, right? And it's you know, I clone down a copy of a file that I'm editing, and you do the same thing. You clone down the same file, and then you know, I'm editing a piece of function, and you happen to be editing the same exact function, right? So if we edit separate functions where you edit a function B way down here in the code, and you update function A that is way up in the code, right? The GitHub will be able to merge those changes and put them all together. But if we edit the same exact lines, right, GitHub is going to complain and say, wait a minute, there's a conflict. There's a conflict. Which one should I take? It won't be obvious what it should do. Okay, so transactions allows to say, well, wait a minute, you know, I am going to be working maybe on a section of a document, say nobody touch this, right? Because you know, it makes no sense for folks to look at data that is not done yet, right? Or work that is not done, it's in progress. You know, I would like to be, you know, exclude everybody else and be isolated so I can work independently. And then once I'm done, I can commit those changes, and then folks can actually use it. Yeah, so it makes sense to isolate folks, right, on certain parts of a document or table or records and whatnot. So transactions allows us to do that. Allows us to say, hey, I'm starting a transaction. I want to have like my own space where I can do all my work. Once I'm done, I'll share with everybody. Okay. Meanwhile, everybody's looking at the current work, the current values of the database, and I have my own little cache, my own little copy of the database where I'm making all my changes, and nobody can see those changes until I commit those changes, and everybody else can see them. Make sense? So yeah, so let's play around with transactions. So to simulate this, right, we're going to create two users in the database, right? We're going to create user A and user B, or user 1, user 2, doesn't matter. And then we'll create two separate connections, right? So from Workbench, we'll create two connections that are going to connect to the same server at the same time, logged in as two different users, right? And one user is going to be making changes, whereas the other user is going to be an observer, right, of what's going on, right? And we like to see, right, whether you're in a transaction or not, whether you can see the changes or don't see the changes until you commit or roll them back or whatever happens, okay? So here it is. So the first part is we're asking you to create two users, which I already done. So here we have, if you go to, let's close, if we, where is my left-hand side? Oh, there it is, okay. If you go here in management and you go to users and privileges, here's where you can create new users. If you click on add account, you can create two new users, users 1 and users 2, or user A or B, whatever the assignment says. And that's what I've done here, user A and user B, right? And I've used the same username and the same for the password, all lowercase or all uppercase, whatever, right? I would use all uppercase. I guess it's easier to just follow. And so both username and password the same, or whatever you remember, right? Make sure you don't forget. Once you've typed in username and password, you'll need to give them administrative roles. So a DBA, if you click on DBA, it'll select everything and give these two users, you know, God powers here in the database, right? And you're gonna save and apply, create those two users. Yes? Once you have those two users, you're gonna create two separate, connections, right? One is going to be a user A connection and a user B connection, right? So you can click here on the plus here, and then you can create here a connection called user A connection, user B connection. You'll need to provide the host name, the port, and the username. This is going to be your user A, and then password user A as well. So you create two connections, one with user A, one with user B. So you're going to end up with two connections, right? So if you click on it, it'll log in as user A, and then here you're going to log in as user B, right? So here you have 2 live connections to a database. Okay, we can close that one. And here's where we're going to be doing our, we're going to play around with transactions. Okay, so what are we going to do? We are going to, I'm going to close this. And we're going to have user A do most of the work, and we're just going to have user B be a bystander, right? They're going to be just observing what user A does and see what user A can see and what user A cannot, I mean, user B, what they can see and what they cannot see, okay? So from user A, let's get started. So user A is going to add. Now both works, you know, as user A interacts with database and user B interacts with database, right? We're going to keep two files open, right? Let's close this. Let's close that. So we're going to have these 2 files open, right? I'm going to be typing most everything, right? Now, user A is going to be doing most of the work, right? User A is going to be doing most of the work. User B is mostly just going to read and looking at the. So user B is going to be less interesting, but nevertheless, we want to just copy there to see what the user B sees. Okay. So anyway, so first we're going to add a brand new field to the blocks table, right? We want to add this new field called add revenue. Add revenue at the blog level. You know, imagine you're writing a blog, right? And the blog has a whole bunch of ads running in the blog, and that is generating a revenue stream for the blog. And we are recording at the blog level. We are recording how much revenue has come in for all the blogs, right? So it's just going to be a field. It's going to be float. Okay, and we're going to record there how much money have we made so far. All right, so we're going to, now this in this case, we don't really care which connection you use, whether you use the user A connection or user B, doesn't really matter. I'm going to do all the work in user A. I'm just going to post this here, paste it. It's a little bit too big. Okay, so I'm going to select that. I'm going to run that. Okay, so this is adding field add revenue to the blogs table. Okay, it's done. If we look at blogs, right, look at the content, you'll notice now that not only we have 400,000 records, but now we have an add revenue field, right? That wasn't there before. We just added it. Okay. All right. Let's maybe we could copy that in here as well. Okay. You see that we have 400,000 records and we have a new column. Okay, so let's go back to the instructions. We're now going to initialize the revenue for a specific blog. Doesn't matter which one. I chose blog ID number 3. If it doesn't, you know, if you can choose a different blog. Let's see. There's a question on the chat. What is the? Oh no question. Let me copy that. Let me paste that. So now we're updating the blog, right? And I'm modifying the ad revenue to be $100,000 for blog number 3. So I'm going to select that. I'm going to run that, and it's successful. Notice that I can now retrieve the ad revenue from blogs where ID equal 3. Right, I can see my change. I can run that, and it comes back to 100,000. Yes, and if the other user will be able to see the same thing. Right, if I copy that, right, if I copy this, you know, run it from the other connection, they both see the same thing, right? Which makes sense. They both see that the ad revenue on blog ID 3 is 100,000. Makes total sense. Okay, we are both looking at the same connection, the same database, the same schema, right? And we can see the same information, which is the whole point, right? If we can both see the same information, what happens when we start modifying the information, right, at the same time? Which one's going to win? Am I going to win? Are you going to win? There should be some way to isolate ourselves, right? Do all our work, right? And then perhaps merge that content together. And that's what transactions allows us to do. Okay, so let's go back here. And what we're going to do here is that, we see that both see the same information, 100,000. Okay, but we want to isolate ourselves and say, wait a minute, I don't want you to see the changes that I'm going to make, not yet anyway, not until I'm ready. Okay, so to do that, we can start a transaction in connection in the user A connection, and any changes that I make under that transaction are going to be invisible to everybody else outside of the transaction. Right, so I'm going to copy that. And so from user A connection, I'm going to start a transaction. I'm going to run that. So the transaction has started. Anything I do here will only be for my eyes only. Nobody else can see it. Right. So for instance, if I update, right, if I update, right, so I update my revenue to be, $50 more, right? A new ad ran, and I just made $50, right, over the day or so. Maybe let's make it a little more interesting. Let's say 5,000. Okay, so let's run that. Okay, and I can see the change went through. Let me remove the result. So I'm going to run that, and indeed I see that I have now $105,000 in revenue. Right now, user B connection, I'm going to run the same exact query, right? And notice that I still only see 100,000. So I do not see, unlike before where we both saw the same information, now user B does not see the same information, right? It sees the actual current value of that field, right? Whereas user A is independently working with its own little copy, right, where that has not yet settled, right, has not been made permanent yet for everybody else to see, right? They're working in their own little world, in their own little bubble, okay? And they could actually, after they do this insert and this update and they do all sorts of things in the database, and they could do something fairly complex. At the end of the day, they might say, oh, no, you know what? All these changes I've been making all day, I just want to throw them away, right? I want to go back to where I was, right, when I started the transaction. It's like a spawn, a respawn a spot, right, where you say, okay, this is where I would like to go back. If I die, I want to go back and respawn at a specific place, right? And so you can roll back and say, just throw away everything I did, go back to my respawn position, right? So I can say roll back. I can roll back from user A, right? And just say roll back right here, just roll back. Okay, and then I can select again and see that I am back where I left off, back to where I was, as if this never happened. It's gone. I am back where I was before I started the transaction. Make sense? Right? And obviously we both see the same thing, right? Both user A and user B again see the same thing. All right, so but what if I did all my changes and I was actually happy with my changes, right? Where I'm going to start a transaction in user A, right? In user A, we start the transaction. So here, right, we start the transaction. Okay, we update, and now we made $15,000. We start for $15,000, and we check to see our revenue, and indeed we see that we have now $115,000. Okay, whereas user B still is completely unaware of what you're doing, right? It still sees only $100,000, right? So user A, after a while, after doing all these updates and inserts and doing all this work, they want to save those changes and say, okay, I'm ready, I'm good, I'm happy with what I have, I'm going to make the changes permanent, right? So to do that, user A can use the commits command. You can do the commit command, right, to make the changes permanent for everybody else to see. So now, they commit the changes that we see. It's obviously the same, 115,000. But now it's not only I see it, but now everybody else sees this as well. If you go to user B and you run your select statement, notice that also user B sees $115,000. Okay, makes sense? Right, so yeah, transactions allows us to create these separate working spaces, right? So that, right, we don't trample over each other's work, right? And it's very important for maintaining database integrity, and making the data be consistent, right? So that, especially when you have multiple users, multiple folks using the same database, the same tables and whatnot. Okay. All right, excellent. So that's the assignment. You're gonna save all the work, right, into user. I think I called it user blogs, user A blogs or something. Yeah, user A blogs and user B blogs. Well, user B blogs is just going to be a select, right? That's all user B is going to be doing, but user A is going to be doing a lot of all the things, right? So now that we have shown you how to do it with blogs, you're going to practice it on your own, but for the posts. So for the posts, right, you're going to do the same thing, right? You're going to add a field called add revenue for the post. So this would be the ad revenue that each blog might have accumulated, right, that have brought in. And then at the blog level, you might have like an aggregation of all the revenue for the blog. So we're going to keep track of ad revenue per post. You're going to initialize it to some value. You're going to confirm that the value can be seen by user A, but not by user B, right? So you're going to confirm that. User A is going to roll back their change and you can confirm that the value went back to what it was before you did the change. You're going to start all over, and then as user A, you're going to start a transaction, set it to some other value, but this time you're going to commit. You're going to commit the change, and then you're going to confirm that both user A and user B can see the change. Okay. All right, so that's you're going to save both SQL in separate files, right? And you're going to submit them as deliverables. And I haven't written the deliverable down below, but I'll make it available. But basically, it's all these files. You're going to submit them as deliverables. Okay. All right. Any questions on the assignment? All right. So if no questions, let's now go and take a look at the slides. The slides are going to walk us through, all the theory behind everything we've just discussed, right? And we'll expand on it and see a couple more edge cases, other things that we need to consider. Okay. All right. Let's talk about indexing. All right. Okay, so let's talk about indexing. So in database indexing, as I mentioned earlier, right, is a mechanism that can improve performance, right, when we retrieve data from a database, right? But we have to be careful, right? Not always that can improve it. It can actually work against us. So we need to know when to use indices, how to use them, and just be careful, right? So database indices are not always the solution for everything, right? So you have to be careful. So the general idea is that in general, right, the more you organize data, the more structure you give data, the more effort you put into organizing your data, you will reap those benefits by making the retrieval of that data much more efficient. Okay, so it turns out that our parents were right when they would walk into our room and see the mess, right? They would say, "How could you find anything in this room?" Right? It's a huge mess. There's it's a you can't find anything in here, right? If you put some effort into that organizing the mess, you would be able to find everything, right? Now, obviously, that somebody's mess is somebody's structure, right? So definitely where somebody might not see a pattern, somebody else might see a pattern, right? So in general, if you had seen algorithms course, you might have run into you might have discussed the performance or the big O notation, where the certain algorithms have a particular cost, either in time or in space. And so you might already be familiar with some of these nomenclature. And so, for instance, in general, if you look at the algorithms that search through a data structure, for instance, an array or a linked list, searching for an item in the list, we say that the effort that it takes you to find something in that list, in general, it's linearly proportional to the size of that list or array or set or collection or whatever. Okay, that means that if you took 50 steps to find something on average, to find something in a list of 100 elements, right? So if you're searching for something in a list of 100 elements, it might take you on average 50 steps to find something in that list, right? And so if you double the size of that list, in general, you will also double the effort, right? And so if it took you 50 to find 100, now it'll take you 100 to find in a list of 200. So you double the effort if you double the size, okay? That's if you put no effort whatsoever to organize your data, right? But if you went through the trouble of organizing your data, for instance, you might decide to sort the data, right? You might sort it alphabetically or numerically or somehow, right? Now you can use much more efficient algorithms such as binary search, which what they do is that they can start at the middle of the data structure of the list, and then quickly decide that what they're looking for is either on one half or the other half of the search space, right? So they can, each time they compare, right, every time they make a comparison, they can quickly say, oh, I'm going to forget about half of my search space and I can concentrate on the other half, right? As opposed to in linear search, every time you do a comparison, you still have n-1 comparisons to make, right? So the first comparison that you make, now you still have n-1. The second comparison, you still have n-2 comparisons to make, right? Whereas in a binary search, you start at the middle and you make one comparison, you quickly just completely ignore half of the search space. You can focus on the half, and then you half again. So every time you make a comparison, you half. It makes it very, very quickly to zone into what you're looking for. And so this dramatically improves the performance, right, of looking for anything. So comparing it to linear search, so say linear search took you 50 steps to search a list of 100, and it will take you 100 to search for a list of 200, right? So you double the size, you double the time. Whereas in binary search, right, if it took you 50 steps to search through 100 elements, well, if you double the space and you say, well, now I have 200 elements, well, your search time is not going to go from 50 to 100. It's not going to double. It's going to go from 50 to 51. You just need one additional search comparison, right? Even though you've doubled your space, right, you only need an extra search, an extra comparison. So that's dramatic, right? You went from doubling your time to just having an additional comparison, right? So that's huge, a huge efficiency. But that's nothing compared to the next one, right? Hash search, right? In hash search, you kind of solve the problem of searching. Basically you remove search. There is no search, okay? Right? The problem with searching is that you have to search. Imagine that you knew where everything was. If I was fixing my refrigerator the other day, and I was putting stuff where they went, and if everything has a space, right? A place, and there's a place for everything. So everything in its place and a place for everything. Where is anything? Well, where there should be. If you know where it should be, then there is no search, right? You can jump immediately and get at what you're looking for, right? And the way that this is done in a hash is that you use the whatever it is that you're searching for, whether it's a last name, whether it's a phone number or an email or URL, whatever it is, you use that as a key, as a key into a hash table, right? So that if you search by an email, well, that email is already hashed into the table, so you just jump to the location of where that content is, right? There's no search, right? You use that as an index into the hash, right? So you can completely skip over having to search for anything. There's no iteration whatsoever. There's no splitting. There's no nothing, right? So if it took 50 steps to calculate that hash and jump to the location of where you find something, on a list of 100 items, well, if you double the number of items, you will still only need 50 steps, right? If you triple 300 or 1,000 or 10,000 elements, it will still only ever take you 50 steps. Okay, so basically you've made your effort independent on the size of your search space, right? Not quite, but almost, right? So we say that the search space, the search effort is order 1, right? Or order constant time search, meaning it takes you always the same amount of time to search, regardless of the size of the search space, which is perfect, right? So databases use these two techniques, right? Of organizing data in terms of these tree-like binary structures, right? That allow you to search and sort the content by a particular key or by a particular index, right? It allows you to apply binary search, right, using tree-like structures, but also applies hashing, right, to be able to jump real quick and retrieve that record very, very quickly. So databases use a combination of these two techniques to improve performance dramatically. Okay, as opposed to doing a full scan of the table, right? Or just iterating over each record looking for something. You can just jump, right, really quick to the record that you're looking for based on what it is that you're looking for. Okay. So yeah, so here's the analogy we had used earlier, right, of phone books, right, where sometimes you're searching the phone book by phone number or searching it by last name, right? I don't know if you remember what a phone book is, right? In the age of cell phones and Siri and Alexa, where you had a list of folks listed in a phone book, and typically you would search by last name, and usually the phone was organized or sorted by last name, which allowed you to apply binary search on the phone book and quickly find the person and see what their phone number was or their address or whatever was listed in the phone book, right? But if you had a phone number instead of the last name, the phone book was useless to you because it was organized by last name, right? Might as well have to use linear search, right? If you have a phone number as opposed to a last name. So ideally, you would have the phone organized by both, right? Organized by last name and organized by phone number. So you can, depending on what you want to search by, you would use one of the index, one or the other. Yes. So you need to have, by whatever you're searching by, it's a good idea to have the index by whatever it is that you're searching. Yes. We want it to be keyed off of by, or keyed by that particular field. Okay. Yeah, each table can only be organized one way, right? Either sorted by last name or sorted by phone book, and so you need a copy, or at least a small version of a copy that is sorted or organized by that field, and then gives you access or references to the original document, right? Just like an index of a book at the end, right? It's organized by term, alphabetically ordered, right? And then you have the numbers of the pages that allows you to jump to the location in the original document, the original book, right? And it's sorted by the alphabetical by term, but you might want to organize by different ways, right? By chapter or by scientific term, or whatever it is, or by author that published the that particular article in that book, right? And you might have many different indices, right? One, depending on how you want to search it. You want to search it by author, you want to search it by year, you want to search it by term, you want to search it by whatever, right? So you might end up with multiple indices. So same thing here, a table, a database table, you might have multiple indices on that table, like we did for the assignment. We have 3 indices that we added, right? One was, I think one was type, status, and country code. We've added 3 indices, meaning there were 3 copies of the same table, right? But organized in different index in different ways. Now these tables, these additional tables, usually are smaller, right? They don't contain the entire data, right? They only have the field and the column by which they are ordered. And then they'll also have a reference, an RID, a reference identifier that references back to the location of the original record, right? The records typically are stored in a file system, right? And the indices will have the location of, the block of where the record is found in the file system, so that you can jump and get the original record directly. Very much like an index in a book, right? You'll have the number of the page, right, of where you would jump in the table in the page in the book of where you can find that term or record in the book. Okay. So yeah, so indices are a copy of the original table, which are smaller, which will have the index values plus a record identifier of where you can find the original record, right? Like a pointer in memory of where that is. To create the index, right? There's you can, in SQL you would say, add index, with it, and then the name of the index on a particular table and the field on that table, right? Or other databases use the command create index as opposed to add index. And then here's an example of creating an index on table major. I'm sorry, the name of the index is called major index on a student major ID. Okay, so we're creating an index on that particular field. And here's another one. We're creating an index on the student ID. Okay, so notice that both of them are on the same table. So 2 different indices, one on the major ID and the other one on the student ID. Okay, now the difference between these 2 indices, right, is very, very drastic. So one of them is an index on a foreign key. Okay, that's very important, right? That foreign key, because you can have multiple students are under the same department, right? The values for this field foreign key is going to repeat multiple times. You can have 3, 4, 5, 10 thousands of students in the same major ID. So this major ID field can be, it's not unique. The value in that index is not unique, right? And that is going to affect performance dramatically, okay? As opposed to this index is on a unique identifier, right? A unique field, which is a primary key, and this is going to give us the most performance boost, right, than any of them. So definitely unique identifiers, unique indexes on unique fields gives us the most performance boost, whereas indices on non-unique fields gives us the least performance boost. Actually, depending on how our data is structured, it actually could perform worse than if we didn't have an index, right, on non-unique keys. Okay, if you want to search something by a non-unique field, right, it might be that it's cheaper or it's faster to do a full table scan than to use an index, right? And we'll see examples of that, of how that might happen. Yeah, so we have unique and non-unique keys. So here's an illustration of what it might look like, right? So here on the left-hand side, here you have the student ID index, right? That have references to the original record. So in the middle here is the table. So the table here has the IDs, the name of the student, it has the year that they're graduating, and they have the major ID here. This is the foreign key that references the department table. Yes, so 10, 20, 10, 20, 30, 20, 30, whatever, right? And this is the primary key here, 1, 2, 3, all the way through 9. Okay, so the indices are smaller versions of the same table that contain the The index values 1 through 9, and this one goes 10 through 30. And then pointers, right? References to where the original records were. See that? Now notice the difference, right? The unique identifiers, all these values are unique, and they are pointing to unique records, right? Whereas in the major ID, right, notice that you have repetitions. You have 10 repeated 3 times, 20 repeated 4 times, and 30 repeated twice, right? And they're pointing all over the place, right, in different portions of the record, of the original records, right? Some at the top, some at the bottom, which is very, very important, right? Which is going to be detrimental to the performance when we search using the major ID index, okay? It's going to be detrimental, not as performant as the student ID, but in some cases worse, right, than if we even had the index, right? And we'll see those examples. Right, so B trees. So B trees are special binary trees that the database creates for us so that it can apply binary search, right? So binary search, remember, allowed us to take a search space, right? And because the data was sorted, right, we'd be able to every comparison that we made, we would be able to throw away half of the search space and then focus on the other half, right? Now our table, right? When we create the table, that table not necessarily is sorted in any particular way, right? It's generated randomly. You should never assume that the table is organized in any particular way. The indices could be organized, right? But not the original bulk of the table, right? So you could have records just randomly put in there. So you have hundreds of thousands of records that have been added, removed, updated over the years, right? And they could be all jumbled up in different places in the database, right? What we could do is that create separate structure like a tree that organizes the indices, right? Whether they're phone numbers or last names or emails or whatever it is, we can organize them in a tree, right? So that if we're searching for a specific email, right, the tree is organized in such a way that the email at the top, right, is kind of like the halfway email amongst all emails, right? And if you're looking for a particular email that is less than the email that is at the root, then you would focus on the left-hand side of the tree. If you're looking for an email which is bigger than the email at the root, you would focus on the right hand of the tree, right? And then you would reapply that algorithm over and over, splitting until you get to the leaves, right? And when you get to the leaf will say, this is the actual record, right? And it points to the actual record in the table, right? So whatever key, right, you would compare whatever you're searching for against the key and then head over on the left or the right, right? Comparison, if it's less than, you go one way. If it's greater than, you head over the other side. Every time splitting, right, halving our search space, throwing away half of our search space, okay? So it definitely gives you the logarithmic kind of performance, right, which is very steep and then very, very shallow, that every time you double the search space, you're only adding one extra query, one extra comparison, right? So it's a dramatic performance boost, right? As opposed to doing a full scan. A full scan, we mean that we're literally going one record at a time, in linearly, one at a time, right? Looking for whatever it is that we're looking for. So full scan, it's equivalent to doing a linear search, right? Just line by line, right? Taking one at a time, and then the cost of searching through this is proportional to the size of the table, right? If the table has twice as many records, it'll take you on average twice as long to find something, as opposed to instead using binary here, right? If it's twice as big, oh well, the tree can be one height higher, right? So that it can cover twice as many elements, but you'll only need an extra comparison, right? Only one extra comparison, as opposed to doubling comparisons, right? So these slides are just illustrating how trees are created. You're not going to be asked about building these kinds of trees. They're just illustrating how these trees are built. Basically they're designed in such a way that they're always nice and full, right? That they're nicely balanced, so that the nodes on one side of the tree have as many nodes on the left and right on both sides of the tree. So they're nicely balanced as opposed to being skewed on one side or skewed on the other, which would cause certain elements to take longer to search, right, as opposed to some other elements being faster to search. So you want some with them to be balanced so that the height of the tree gives you the performance on how many comparisons it'll take you to find anything to go from the root of the tree down to the leaves. That will tell you how many comparisons you have to make to find whatever record you're looking for. Okay, so the height of the tree tells you how many comparisons you'll need to go from not knowing anything, going all the way down to the actual record of whatever it is that you're looking for, right? So these trees also, each node in the tree contains several keys, right? And those are linearly searched, right? You have to compare how many elements you have in that array of keys and find which one is the one you're looking for, right? But then once you find those, you go down the height, and that's a comparison to the logarithmic performance that we've discussed, right? So in here, for instance, we have 3 levels, right? We have the root, and then you have several branches down below. And notice that to go from the root down to any leaves, notice that we only have 2 comparisons, right? We go from 19 down to 5 down to 2, right? Those are 2 or 3 comparisons to go down from the root down to the leaf. So any leaves, right, only takes 2 or 3 hops to go from the root down to the leaf, right? So the performance here is that you would only need just 2 or 3 comparisons to find any of these 20 or 30 elements, right? This just illustrates on how these trees are built. Basically, they are built from bottom up, right? You start at these new elements as you insert them into the tree, right? To trickle down to the leaves, finding where it would fall. And notice that 28 falls nicely between 27 and 29 over here, right? So it sees that it's not 28 is not between 13 and 24. It is between 24 and 30, right? And 28 would fall under there, and then it would find where it would go in that array, right? So notice that all the numbers to the left of 13 here are all less than 13. All the numbers between 13 and 24 are between down below here, 14 to 22. And all the numbers between 24 and 30 are down here. Okay, so B trees are built this way, right? So when you insert and there's a space for it, it will modify the array, right, to fit in the new value, so it's already sorted. If it doesn't fit though, right, so that for instance, if we're inserting 8, so 8 would go before 13, so it would go down in here, it would be before 13, so it would go at the end of 7, but because our nodes can only hold 4 elements, right, it would have to break into two arrays, where half of the original values go in the new array and 5 and 7 go in the other half of the array, right? So, and then 8 would go where it belongs, 8 over here. Here's another example of going 20. 20 is between 13 and 24. It would fit in here, but it doesn't fit, so it would split. It would split into 2 additional records so that you can insert number 20. Okay. So anyway, what it does is that it splits, and then it pushes up, any of these items, so that they are in between the correct values at the parent level. Okay. Anyway, so here's just a couple of other examples of inserting. Yeah, we're not going to ask you to build these trees, and just letting you know that these are the structures that databases use to organize their data underneath. Okay, so let's take a talk about the performance on how index affects performance, right, in different operations such as inserting or selecting, and different types of select statements, right, and whether if you're retrieving data based on a unique index or a non-unique index, like the student ID and the major ID that we declared earlier. Okay, so So let's get back and remember that we had created two indices, a non-unique index, major ID, right, and a unique index, right, the student ID, right. So this is a non-unique, this is a unique index. So both of them. Okay, so imagine we want to retrieve data, right, using for instance a query on the student ID or a query on the major ID. What would be the performance differences, right? If we do it on the student ID equal 10, well, that would be an individual record, right? That would come back, one single student record that has student ID 10. But on major ID 10, right, that might be actually multiple students that would come back, right? Multiple students would have major ID 10 because it's non-unique, right? So this is the graphically what the data that we have. So what happens if we're searching for a specific record, right? A particular student whose ID is 8. What would happen? Well, if we had no indices, right, we would have to do a linear search, right? We would have to look at record 1. If it's not equal to 8, we throw away 2, 3, 4 until we find, until we find student ID number 8. Now this student ID, it could be the very first one, it could be the very last one. Okay, so we might be really, really lucky and we find it right away, or it could be very, very unlucky and it'd be the very last one. Okay, but nevertheless, right, it will be proportional to the size of how many students we have. Okay, so if we instead have indices, then we would use the tree, right? We would compare our 8 against the tree, and the tree might have to do maybe 2 or 3 hops down into the table, right, until we reach the index table, and then it would then tell us how to jump to the actual record and tell us, oh, here it is, right? Here's the original record. We would not be able to do a full scan. It would take us 3, 4, 5 different comparisons to get from the root of the tree down to the leaf, right? And then we can just jump into the actual record. No need to do the full scan, okay? So we want to compare how much better is one versus another, right? But before we do that, we need to decide what it is that we're comparing, right? Now, I've been discussing a lot, saying that it's that we're saying, oh well, how many comparisons do we need, right? How many comparisons does it take you to do either a full scan or use a tree? And so that we have to realize that it is not the number of comparisons that we're trying to optimize, right? Because comparing for a CPU, that's a very simple thing to do, right? But this data, right, the CPU only has access to any data that has been read from the database, right? The database might contain, many millions of records, of which the CPU can only look maybe at a handful of them, maybe a couple thousand records that are stored in RAM, right? So the CPU needs to be able to copy any content that is in the database, copy it over into RAM, and then iterate and do the comparisons, right? Now, the cost of doing the comparisons is negligible, right, compared to the cost of going out to the file system, right, and copying that content from the file system onto RAM, right? That's very, very expensive. It's several orders of magnitude much more expensive to go out to the file system. So really, that's what we want to optimize, right? That's the cost that we want to look at and see how could we improve that, right? And so we need to think about how is that data is actually stored in the file system. Usually the file system is organized in blocks, right? And each block will have so many bytes, and then in each record or each block might contain multiple records, stored in a block, right? Maybe 10, 20, 30 records, depending how big these records are, might fall in one single block. So we want to compare, well, how many blocks are we reading or writing? And that's what we want to minimize, right? The file I/O. So let's consider some generic values right? Some realistic values, and see what those costs might be on file IO, not comparisons, file IO. So say you have a university, you have 40,000 students. That's not unthinkable, right? And you have 40 departments. So on average, we might, just to make a ballpark, you might say that 40,000 students, 40 departments. On average, each department might have maybe 1,000 students, right? That makes sense. And we can say, and let's further consider that each block, maybe it's big enough to hold maybe 10 records, right? 10 students per block, right? So the question is, when you're looking for a student or a whole bunch of students by major ID, by student ID, how many blocks are you reading? Not comparisons. I want to see how many blocks are you reading, because that's what's expensive, not the comparisons, right? So if it's 40,000, right, and we're doing a full scan, right, and there's no indexes, what would happen? What would it look like? Well, it's 40,000 students, and there would be 4,000 blocks, because there's 10 students per block. So if you're reading the entire table at a worst case scenario, right? Worst case scenario, you're looking for a student, and the student is the very last one. So you need to read the entire table into memory. So you'll end up doing 4,000 block reads into memory, right? From the file system into memory, right? So worst case scenario, you're doing 4,000 reads, right? Now, if you compare that against doing an index search, right? The index search you might need several reads to go out into the to read the tree, right? And do the comparisons going left, right, left, right, left, right, up until you get to the final record, right? That'll be another read. Then you'll need to read maybe the record identifier, right? Which will be a pointer to the actual block where you find where the actual record is found, right? And then you maybe need to read that block into memory so that you can do the comparison and look for the actual record and find it. So, it might be maybe 3, 4, 5 reads. I don't know. Okay, on average, right? So let's say it's three reads. So if it's 3 reads, right, to read the tree structure into memory and do the comparisons and then jump to the record, I mean, you're looking at 4,000 reads, right, as opposed to 3 reads if you're using an index. So you're talking about thousands of times faster, right, if you're looking for an individual record, right, and going against an index versus a non-index implementation. Okay, so this is dramatic improvement when you're looking for an individual record, right? But this is not always the case. Okay, this is not always the case, and this is a graphic representation of what's happening, right? You have 4,000 records broken up into 400 blocks, right, with 10 records each, right, and then you're doing full scan, reading 4,000 blocks, right, 10 records each into memory, right? So yeah, let's now consider the non-unique index, right? Major ID. Major ID is not a unique index, right? That means that if you do this query where you search a student, give me all the students for major ID 20, what's that going to do? That's gonna say, well, okay, well, that's if you give me a particular major ID and I know there's 1,000 students per major, right? That means that I'm going to end up going 1,000 times to the file system, retrieving individual students, 1,000 students, 1,000 reads. Okay, right? And so as I iterate over these students, right, I have to read 1,000 blocks into memory. Okay, and so the dramatic the improvements in performance are not as dramatic, right, when you use non-unique indexes, right? Because with full scan it took you 4,000 reads, right, of blocks, whereas in if you're doing using a non-unique index like major ID, it took you 1,000 reads. It's still 4 times improvement, but not the 1,000 times improvements where you're doing a unique index, right? So if you don't get as much a boost in performance as when you have a unique index when you're using non-unique indexes like major ID. Okay, and part of the reason is that when you have a unique index, right, you know exactly where to go, right? You go out down to the leaf, and then you just jump to where it is, the record identifier. You can retrieve that record, and you're done. You're all set. But if you're doing a non-unique index, you need to do that for every single student that you find, right? And you are missing on part of the efficiency of, if you're reading one block into memory, it could be that in those 10 students, best case scenario, you have 10 students in that major ID, right? And you would keep them all, right? If you would compare all 10 of them, you would find, oh, they are all in the same major ID. I have just saved myself, right, 10 reads or 9 reads, right? With one single read, I found 10 of them, right? So I don't really have to do 9 to find the 9 other students that are in the same block. But because I am not doing linear search, because I'm not scanning the table, right? I only know that I found one single record in that one block, and then I throw it away, right? The next student that I find might live in the same block I just read, okay? And I'm going to read it multiple times, right? I'm going to read it in again, right? Even though I just had it, I threw it away, but there's no way for me to know, right? Because I only care about that one record identifier. It tells me that which one it is, right? It has no knowledge, right, that there might be other records in there. So there's some inefficiencies of multiple times reading the same block because I have no way of taking advantage of that, right? Ideally, I would be able to combine both strategies, right? Where I use an index to jump into the block, and then I could also combine it with a scan, right? That actually iterates over all the records in that block, right? So that I could, identify them and not misuse, right? And miss an opportunity to use that read more efficiently. Okay. So anyway, we will keep discussing this later on Friday, where we're going to be talking about cases where actually adding indices performs worse than a full scan. Okay, and we'll see what the edge cases might be where that might occur. And this is only in particular for non-unique indices. For unique indices, it's always going to be better to use indices, right? But for non-unique indices, you have to be careful, right? Not always performance will be better. Sometimes it could be worse. Okay. All right, everybody. Any questions? All right. Thank you, everyone. Yeah, don't forget tonight, 7:30. If you have questions, if you need help with the assignment DB7, DB8, please come by and we can take a look at it together. All right.
Thank you, Professor. Have a nice day.
All right. Take care. You too. Bye-bye.